I'm going to talk about our work in uncertainty quantification. It's only a half hour, so I'm going to present some highlights, but I'm happy to answer questions or follow up with emails. We have worked for a number of years on being able to establish uncertainties in model predictions for large computational models. And this, in the universe of the Department of Energy, is a significant area of activity today. You can imagine the kinds of codes we're talking about, and that we have to be sure about their validity and the quality of their predictions. So I will cover some brief introduction and then move on to talking mostly about the forward propagation. In fact, you in this audience deal a lot with the inverse problem. I will talk a little bit about it, and I will close. So first, why do we bother? I think whether you come to this from a scientific perspective or engineering perspective or decision maker perspective, you ought to recognize that being able to put error bars on predictions is an important thing. You can argue for the need for establishing confidence in predictions simply for predictive design, for validation, for optimizing design under uncertain operating conditions. Anytime you need to rely on predictions for decision support, etc. Yeah. So I think the justification should be quite clear. And now, in principle, the computational paradigm you can think of, we have a computational model. You have some set of inputs that you know, and you use it to predict forward prediction. Of course, this picture raises the question, where do the inputs come from? So the inputs usually come from some type of measurement, from data. And since data is noisy, in principle, this means that your inputs are uncertain. And so you have uncertain inputs, and this means that the outputs of the model will also be uncertain. And you need to be able to tell me how confident you are in the predictions. So in this picture already, we have both the forward and the inverse UQ problem. The inverse UQ problem is essentially fitting, but in a statistical context. So it's a statistical inverse problem. You have data, and you're trying to establish values of parameters of some fitting model with quantified uncertainty. The forward UQ problem is taking uncertain inputs, pushing them through a computational model, and getting the outputs out. So uncertainty comes through data in this way, but also whenever you have a prediction, ultimately you might have other data sets to validate, to compare one model against another. And here again, noise comes into the picture. And the comparison of different models is nothing but a hypothesis testing scenario. And so here we're talking about a statistical hypothesis testing scenario with uncertainty. So uncertainty permeates the whole activities that ultimately we need to go through for computational modeling. So I have one slide on a computational perspective, although I'll talk a lot about algorithmic issues going forward. But from a computational perspective, it's first important to stress that UQ will involve many times the cost of an individual simulation. So that has to be clear. In other words, you cannot plan to estimate uncertainties in a model that one realization of stretches all of your computational budget, right? So you don't want to be in that scenario. On the other hand, it enables a lot of information to be extracted from the system. So aside from questions of uncertainty, you can think of UQ essentially as a parametric study, because you are exploring the behavior of the model over a range of variation of your parameters. And this actually is very informative. Many times we find that codes will fail when you go in corners of parameter space because the coders never thought to go in that direction. And in that way, it enhances scientific discovery. Now, computationally, what can we say about scalability and performance? essentially, most practical UQ methods rely on sampling your own forward problem. And so we really relegate the performance largely to your code. On the other hand, sampling has consequences. In other words, if you have a cluster or a supercomputer trying to do 1,000 instances of the same large PDE solve, you have very similar I/O patterns we have, and you can run into I/O bus contention, so you have to watch out for those. It's important to be fault tolerant, of course, to be fault tolerant, and fault tolerance is available in some UQ methods, not in others, and I will talk about some of those. Generally, those that involve random sampling will be fault tolerant. Many other methods require you to be able to evaluate each sample, and so this is something you have to be concerned about. And ultimately, code failures. As I already said many times, we run into the situation where you sample of a parameter space that the modeler gave you, that the modeler gave you the code, and you go into the corners and the code dies, and they have to go back and figure out what's going on. So this happens all the time, and it could be either a bug, it could be a physical set of conditions that they didn't anticipate, etc. Okay, so let's start with the forward propagation of uncertainty. And the first thing you can think of is, okay, you always can do error propagation. So you have a delta x on the input of your model, and you want to evaluate the delta y on the output. What's the big deal? You can do error propagation with the chain rule. Of course, the big deal is that if the model is nonlinear and if the uncertainty is large, then these methods, of course, don't work well. You have to resort to something more global, not local like that, okay? So there's a zoo of non-probabilistic methods to do this that I will not go into. We focus on the probabilistic context. In other words, we represent uncertain information using probability theory. We represent uncertain variables, uncertain inputs, uncertain outputs, all of that using probabilities. Okay. So we want to propagate uncertainty from model input to output using probability. In other words, I can put a PDF, a probability density function, on the model input, and I would like to find one on the model output. Of course, the easiest thing to do is Monte Carlo. You can generate random samples from the input PDF, evaluate the output for each sample, and bin these to get the density on the output. And this is quite robust and very easy. Of course, it has the issue that Monte Carlo errors converge at the rate of 1 over square root of n. And so it's a slow rate of convergence and requires many samples for reliable estimates. And many times, if you say you need order 10,000 samples to get a certain accuracy in predictions, you may be able to run the code only 200 times. So you cannot afford that. And so the advances over the past 2 decades in uncertainty quantification have been, to a large extent, about going around this difficulty. And in fact, the easy way to view how you go around this difficulty is you build a cheap surrogate for f of x, for the forward model. If you can do that, then you can do Monte Carlo, of course, and do it as many times as you like, as long as building the surrogate is not as hard as this problem. And that is indeed the case in many situations. There are methods to basically fit a function to some proposed functional form to your output model over the input space. You could do this by collocation, by regression, and also by Galerkin methods. And this is the part where I'm going to focus on what are called polynomial chaos expansion. And I won't go into any detail beyond a couple of slides on this. But here's the essential picture. So you have input-output map, y equal f of x, which could be your PDE solver, whatever it is. X is a random variable. We want to estimate the random variable y. So as I said, you can describe the random variable in terms of its density, but that's not the only way. You can describe it in terms of its moments. But you can also describe it as it is, which is it is a function on a probability space. And most of the time, in statistics, we don't deal with it directly this way. But in this context, we do. We represent this function. We represent the random variable using an orthogonal expansion, something like a Fourier series, in terms of a simpler set of random variables. So we choose a set of coordinates. Say you have n uncertain inputs. You choose a set of coordinates, and you define a simple set of, let's say, independent standard normals or uniforms, whatever is convenient for you. And you define a function that is an expansion in terms of, sorry, I don't know if you can see this, in terms of these functions of Xi. So these are orthogonal functions. Again, like sines and cosines. In this case, since this is a random variable, they're not. So if you choose a basis that's a Gaussian, then these are simply the Hermite polynomials. Very, very easy. If these are uniforms, then these are the Legendre polynomials. The choice has to do with being orthogonal to the density of the measure. And so representing a random variable in terms of these coordinates as an expansion like this is really about discovering this vector. So you're putting a linear expansion, linear in terms of the coefficients, which are these UKs, in terms of some nice set of polynomial functions. They don't have to be polynomials, but most of the time they are. And so characterizing this random variable in this case is about establishing this vector of coefficients. And of course, the maximum order you want to go to. Okay? So the terminology may look something a little bit involved, but in fact, it's just fitting a function. And in the end, the result is a PC expansion, which is a response surface for model outputs over the inputs of the model. So that's really the important message. You are building a response function that looks like your quantity of interest variation over the parameters. And so the coefficients can be found in a number of ways. You can do this simply by least squares fitting, but you can also do it more effectively by Galerkin projection. And the design of these functions is based on the plan to use Galerkin projection. And I'll show a slide on that. And the key point is, why is this useful? It really is useful because it allows you to use functional analysis for propagating uncertainty. And there's, in engineering, we have decades of experience with functional analysis in PDEs, right? So this is the important thing. Okay. So the strategy for using PC methods for UQ is you represent the inputs as random variables, you establish them as PC expansions, you build PC expansions, and you evaluate PC expansions for the output. And we'll talk about how you do that. It's fast, or it can be fast under many conditions. And from the expansion on the output, you can evaluate everything you want, PDFs, sensitivities, et cetera. So there's some technical restrictions, but most of the time in physical models, we certainly do have finite variance. Okay. So how do we propagate uncertainty given this formulation? And I'll just have this one slide on it. There are a number of ways to do this, but this is an illustration of how it goes about. So the model remains a black box, and we will evaluate samples of the model. But these samples are now not random. They are the quadrature points required to evaluate these types of integrals. See, these are the Galerkin projection integrals. And so what you have inside the integral, every sample Xi is a point in parameter space. You're choosing some sample of parameters at the quadrature points. This is just the density of Xi, which can be a Gaussian. This is the function that you know. So these are both easy. And this is the forward model as a function of the parameter that's written in terms of Xi. So evaluating this integral is really only about designing a quadrature formula and evaluating your large PDE model at the quadrature points. When you're done, you have these coefficients for any quantity of interest. Okay? So this integral could also be done with Monte Carlo. Of course, Monte Carlo is a high-dimensional integration approach. And even though it has a slow convergence rate, it has the property that its convergence rate is independent of dimensionality. I'll get to this point a little bit later. But quite often, to get accurate results with small number of samples, when the dimensionality is controlled, you can rely on a collection of quadrature methods that come handy into this. These can have fast convergence, but the convergence rate does depend on dimensionality. So let's talk about dimensionality. So in this world that we live in the UQ world, dimensionality is probably the most important challenge. So when are you high dimensional? When you have a large number of uncertain inputs. These could be lumped parameters, or they could be degrees of freedom in representing a random field, like a permeability over space, etc. Okay. So PC-based methods, if you go to very high dimensional setting, they will still, despite all the tricks with sparse quadrature, they will still require too many samples. Monte Carlo requires also a large number of samples, but it has a property, really, that while the convergence rate of the error is independent of dimensionality, the constant in front of that, the error itself, does depend on dimensionality, but it depends on the number of important dimensions. And that's the key quantity. It's the effective dimensionality that matters. So you may have a model with 1,000 inputs, only 5 of which are important. It's really the 5-dimensional context that governs the error of Monte Carlo, without you having to know which 5. That's the beauty of it. Yeah. So, and in many physical models, if you focus on smooth observables, you will find that they depend on small number of inputs. And in that context, the trick to deal with dimensionality is to first use Monte Carlo with global sensitivity analysis to identify the important parameters. And as I said, even though you may be 1,000-dimensional, this will work if the model has smoothness. And then once you've identified the reduced dimensional space, you can use highly accurate sparse quadrature on the reduced dimensional space and get accurate estimation of uncertainty. So this is something we rely on all the time. Now, this strategy works, but it can also still be expensive if the model is really big and really complex. Because even with Monte Carlo, for global sensitivity analysis, if you are trying to fit a model that has a lot of coefficients, this PCE model, and you cannot take enough samples, you're going to need regularization. And so we combine Monte Carlo sampling with PCE fitting, with L1 normed constrained regression. So we rely on compressive sensing to discover a sparse model, a sparse PCE. And I think most importantly, we rely on multi-level Monte Carlo methods that essentially use computations at different degrees of resolution. So you combine some fine resolution runs and a lot of coarse resolution runs, as well as multi-fidelity methods, which combine coarse and high fidelity, low and high fidelity models. So you can combine, let's say, 2D and 3D models. And you can bring all of that together, and the amount of computations you need to do at each level depends on how correlated they are. So if the coarse model results are well correlated with the fine model results, you know you can rely on it to capture that quantity of interest well. And so you take more samples. So this is all done adaptively. And so with this set of tricks, you can actually come down to a number of samples of the complex model that is actually achievable. Okay. And the same you can say for the subsequent step when you're doing the forward UQ with sparse quadrature. Multi-level, multi-fidelity methods work into that sampling strategy as well. Okay. So if there's anything I'd like to stress, I think is this point that for really complex models, you need these types of methods. So this is an example in a combustion system. This is a turbulent flow with a methane hydrogen fuel mixture. Reynolds number here, number of mesh cells. I won't obviously talk about any of the physics here, but this is a computation that's expensive. We had 3 uncertain parameters. In this case, it's the Smagorinsky constant and the turbulent Prandtl and Schmidt numbers. And we were able to use 25 samples to get reliable estimates of uncertainties as well as global sensitivity coefficients at specific locations for mean and RMS type quantities. Okay. So 25 samples was enough. This is another example with modeling the flow in the Gulf of Mexico under conditions from Hurricane Ivan. This was a model with 4 uncertain parameters. They had to do with subgrid mixing and wind drag models. And this requires on the order of 400 models. 400 simulations. So the key thing is we're not in the realm of tens of thousands of simulations. We can get accurate estimation with order hundreds of simulations. And in this case, we're looking at the mixed layer depth in the Gulf of Mexico. This is another application. I'll talk a little bit more about this. This is an ongoing work. We're modeling turbulent, multi-phase, supersonic flow in a Scramjet engine. This is based on a design from NASA. And there's data on this from NASA. So this is the experimental rig, and the actual computational domain we use is half of the geometry for symmetry. So this flow is very difficult to compute. It has very high Reynolds number. It has turbulence, multi-phase flow, combustion, all of that. It's a very expensive simulation. And so this has really been a very interesting application to work in. You can see what the system is involved. You have inflow turbulence initially, and then you have injection of fuel at these 2 locations, and then the flame is stabilized in this region over this expansion. Then you have the supersonic exit. It's meant to be a model for a hypersonic engine, hypersonic flight engine. You can see the CPU times and the run times. The type of computations you get out of this are, of course, very involved in terms of detail and associated complexity. But this is where I said we use all of these machinery. So we rely on both 2D and 3D large eddy simulations. We rely on fine and coarse grids on both locations. And so we bring all of these together. We compute at coarse resolution and low fidelity as much as needed to inform the quantities of interest we're interested in. In this case, we have 11 uncertain parameters. I won't go through them. These are stagnation conditions at the inlet. These are turbulent model parameters. And we're interested in 2 global quantities of interest, combustion efficiency and stagnation pressure loss. And I'll just show, as I said, this is something that's work in progress. I'll show results just to indicate the comparison between coarse and fine resolution in terms of quantities of interest. We know, of course, the flow is not 2-dimensional. We know at coarse resolution you'll lose a lot of detail. But the key thing, if you can establish convergence on quantities of interest, you're there. And so here, for combustion efficiency, for example, we have the sensitivity coefficients for each of the various parameters from 2D, D/8 and D16. These are our names for, this is the coarse resolution, this is the finer resolution, and we have D32, et cetera. So basically, we're pointing out that the sensitivities you get are similar. These are the 2 dominant parameters, and similarly for stagnation pressure loss. And small variabilities here don't worry us, because we're only doing this global sensitivity analysis to establish a low-dimensional subspace, which we go after with sparse quadrature, more accurate. OK. So the point is you can get consistent information from coarse results, consistent with fine resolution results. And so you have a lot of gain from combining both of these. OK. And this is the kind of picture we end up with in terms of prediction with uncertainty. These are flow field profiles at different stations, superposed on mean flow quantities. We can predict a PDF at each location for the velocity or quantities of interest that you care about. OK. So does this mean I have 5 minutes left? OK. So I'm going to quickly go through my few slides on inverse Euclid methods. So inversion, as I said earlier, is the fitting part of the problem. You have data, you have a model with parameters, and you want to discover the values of these parameters that best fit the data. But here, we're not only interested in the best fit values of the parameters. We want the joint density on the parameters that tells you how well you know them. Yeah. So I won't go into these details if you don't have data. But most of the time, we say we have actual data. And we rely on Bayesian inference methods. If you know Bayesian inference, apologies for the slide, but basically, this is a very basic picture of what Bayesian inference is about. Bayes' rule is a statement about conditional probability and joint probability. And basically, it's a very simple statement that the density on any two variables, lambda and y, is simply the conditional on y times p of y, or the other way around. And if lambda is your variable that you're trying to measure, and y is the data that you have collected, this is the type of formulation of Bayes' rule that you want. You want to learn about lambda conditioned on having this data. And you learn that from the likelihood, which says basically, if I have my forward model with a given value of my parameter, what type of likelihood is there for the data with my model? How good is the fit with the data? This is the prior density, what I know about the model before I started. And this, for us now, is the normalizing coefficient. I won't get into it. So the modeling effort often for physical modeling goes into the likelihood. For many cases where you have very poor information and very little data, it's the prior that is crucial. So from a computational point of view, we don't deal with analytical densities. We deal with defining a random walk that generates samples from the density of interest. So there's a lot of literature on this. I didn't put any pointers on this slide because it really is old literature. So we rely on Markov chain Monte Carlo methods for generating these random walks. And you basically have a procedure that at every sample requires an evaluation of your forward model and then makes an accept or reject proposition, and then you sample again. And so the key thing is that you need a lot of samples, being a random walk procedure, and every one of them requires evaluation of the forward model. This is why I did all the forward UQ first. Instead of actually relying on the forward model directly, you can use the machinery I talked about before to build a PCE over the parameter ranges. Yeah? So that's a surrogate. You can also build surrogates in other ways. In statistics, it's very common to use Gaussian processes. Today, people are using neural networks. You can build surrogates anyway. And this way, you can do the fitting. So high dimensionality has a role to play here, which I won't go into detail, but I can certainly talk about it. It's a significant challenge. I will leave you with this slide. I talked about most things on this slide. There's a lot of areas that I didn't cover that are important. Basis adaptation and manifold methods, model comparison, model evidence for model selection. All of this is really available in the literature. I suggest, if you're interested, to look at open source tools to codes from Sandia that have a lot of functionality in this context. Thank you very much.
Thank you. We do have time for a couple of questions.
Interesting talk. The question I have is, what is the state of the art to deal with problems that have many application problems actually have this situation, where you have different correlation lengths and variability across in different locations. So how do you deal with those cases?
When you have random fields, basically,
Right.
Yeah. So that's a situation where high dimensionality can certainly blow up. I mean, you have a lot of difficulties first in describing the random field. You know, what correlation length model do you presume? And also, if it's a rough random field, you're going to have high dimensionality. The thing I would say there is, first, there are methods that don't require you to state a correlation or a covariance matrix model. You could build that from the data itself, or you could bypass it and simply build a representation for the random field directly using Bayesian methods from data. Yeah? The other thing to say is that while dimensionality can be high to describe the random field, the quantities of interest you want out of the simulation will not depend well on most of these dimensions. And so again here, if I invoke the power of Monte Carlo, I would argue that if you have a smooth observable, then Monte Carlo ought to be able to discover the dimensionality that is important. And there are methods that use analysis of data, SVD, as well as other methods to analyze data, to build manifolds that represent the underlying structure that's low dimensional, and you use Monte Carlo sampling from these manifolds to enrich the system. So there's ways, I think, around it, but of course it can be hard if you're not looking at smooth observables. Then that certainly, rare events and things like that are much harder.
Please join me in thanking our speaker. And I know you're going to be here, so we can talk to you during the networking. Yeah, okay, perfect.